Okay, this is for the overdamped voltage response, and here we've got a problem set up. We have, this is going to be natural response because we have some initial energy over here in the capacitor at t equals 0, and we've got a 0.2 microfarad capacitor on the left, we got a 50 millihenry inductor in the center, and we got a 200 ohm resistor on the right hand side. Voltage across all of those things is what we're trying to find, and we know that it's going to change over time. You need a little bit of extra information here, so let's say that the voltage at 0 plus is equal to 12 volts, and let's say that the current through the inductor at 0 plus is 30 milliamps. Okay, now based upon this, you might say, well, we know the form of the solution. You better check to make sure that your alpha and your omega fall into the right category for overdamped. Now, I will set it up so that, yeah, this is the overdamped solution, but if you were just approaching this problem without knowing that, you need to test. So let's test it. Let's do alpha is going to be 1 over 2 RC. That's going to be 1 over 2 times 200 ohms times C, which is 0.2 times 10 to the negative 6 farads. If you do that calculation, you end up with 12,500. Okay, now let's compute omega naught. Omega naught is 1 over the square root of LC, and that is 1 over L, which is 50 times 10 to the negative 3 Henry, times C, 0.2 times 10 to the negative 6 farad. And that is going to be 10,000. So since you can see that, you don't have to square anything. What we've got the case of is that alpha squared omega naught squared, the alpha squared is going to be greater. All right. This is the overdamped case. All right. So now that we know the overdamped case, what is the voltage response going to look like? In general, it's going to look like V equals A1 e to the S1t plus A2 e to the S2t. Okay, since we expect that to be our voltage response, then our goal at this point is to figure out these things, A1, S1, A2, S2. Let's do the S's first. S1 is going to be minus alpha plus the square root of alpha squared minus omega naught squared. So that's going to be equal to minus 12,500 plus the square root of 12,500 squared minus 10,000 squared. Do that calculation, you end up with minus 5,000. That's going to have units of radians per second. Okay. Let's do the same thing for S2. Let's do S2 right here. It's going to be minus alpha minus the square root of alpha squared minus omega naught squared. So it's going to be minus 12,500 minus the square root 12,500 squared minus 10,000 squared, and you do that calculation, you end up with minus 20,000. Okay, so there are your S1 and S2 values. All right, we are told that the voltage at 0 plus is equal to 12 volts, so that's given to us. So I go back up here and I say, well, my solution is A1 e to the minus 5,000 t plus A2 e to the negative 20,000 t, and I need to evaluate that at t equals 0. And when I evaluate that at t equals 0, the exponentials become 1, and I'm left with A1 plus A2. So I've got A1 plus A2 equals 12 volts. That right there is one of the equations that I need in order to figure out what A1 and A2 are. But I also need a second equation. So I need to find, in order to be able to do this, I need to find I sub C at 0 plus. Okay, but how do I do that? I wasn't given I sub C, I was given I sub L. All right, nevertheless, we should be able to get there. So we've given enough information that we can figure it out. So let's go over here and think about KCL at the top node. So going back here to look at this, this is I sub C, this is I sub L, this is I sub R. All three of those should sum up to be 0. So at any point in time, that should be true. So I sub C plus I sub L plus I sub R should be equal to 0. And that should be true for any time. So if that's true at any time, then it will be true at 0 for all of these. Okay? So if I look at this, I can see that I sub C at 0, and these, I could put plus signs up there. This is all 0 plus. I sub C at 0 plus is going to be equal to minus I sub L at 0 plus minus I sub R at 0 plus. There. Okay, now I sub C at 0 plus, I was told what that is. I'm sorry, I sub L at 0 plus, I was told what that is, and that's 30 milliamps here. So I'm going to go over here and I'm going to plug in minus 30 milliamps. That's for I sub L. And then minus this voltage here at 0 plus. Well, what is that? I said voltage. I meant current. What is this current at 0 plus for the resistor? All right, well, current for a resistor at any time is just V over R. So it's going to be the voltage at 0 plus divided by R. All right, let's go ahead and plug that in. Minus 30 milliamps minus V at 0 plus. We were told that was 12 volts divided by our resistance of 200 ohms. If you do that, that turns out to be minus 30 milliamps, and this turns out to be minus 60 milliamps. So minus 90 milliamps is what I sub C at 0 is. All right. Now, why did we need that? We need that because I sub C at 0 plus divided by C is equal to S1A1 plus S2A2. Okay, that's what's on the right-hand side here is just dV dt. And this equation is just the relationship between current and voltage for the capacitor. Specifically, this is dV dt evaluated at 0 plus. Okay, so we took the derivative of the voltage function, and we end up with this, evaluated at 0. All right, let's plug in I sub C at 0 plus divided by C is going to be negative 90 milliamps divided by 0.2 times 10 to the negative 6 farads. Let me confirm that that is. Yep, that is it. And that is going to be equal to S1, which was minus 5,000, A1 plus S2, and S2 was minus 20,000, so minus 20,000 A2. All right, so here are our two equations. Let me rewrite the other one. The other one was 12 equals A1 plus A2. So this is our one equation. This is our other equation. If you do, let's see, minus 450,000. I think when you evaluate this, pretty sure you end up with that number right there. So there's our one equation. Here's our other equation. We have two equations, two unknowns, so we can get our A1 and our A2 at this point. You do that, and you end up with A1 equals negative 14, A2 equals 26. Okay, so our voltage as a function of time is going to look like A1 e to the S1t, so that's going to be minus 14 e to the negative 5,000t plus 26 e to the negative 20,000t. And that is volts, and that is for t greater than or equal to 0. So there is our voltage function. There's our answer. We were asked to find V of t. That's the voltage with respect to time. So at t equals 0, it should be 12 volts. And if we go in here and we look at t equals 0, these exponentials are going to go to 1, go to 1. 26 minus 14, yep, that's 12 volts. All right, so it works. It works at least at t equals 0. And it should work for all times beyond, greater than t equals 0 as well. Okay, so we worked that case. That is the natural response for the overdamped case. If you were to graph that, it looks something like this. It goes down and then reaches 0 in the limit. Okay, so that's what it looks like. Okay, now let's say that, let's expand on this problem and say that we needed to figure out what I sub r as a function of time is. Well, you know that that's just going to be V of t divided by r, and V of t is minus 14 e to the minus 5,000 t plus 26 e to the minus 20,000 t, and that's divided by 200 ohms. So you can do that calculation, simplify that, 14 divided by 200 and so forth, and it's going to be minus 0.07 e to the minus 5,000 t plus 0.13 e to the minus 20,000 t amps. Okay. What about, let's say you're asked for I sub L of t. Okay, well, I sub L of t is 1 over L integral from 0 to t of V of t dt plus I sub L at 0. Okay, now we could possibly solve this. You take your voltage function, the negative 14, you take that right there. That's on top of that expression. Plug it in here and do the integral, and you can find that. So you could get an expression for I sub L. But let's pause for a minute, not do that at the moment. Instead, let's go on and find I sub C of t. I sub C of t, that one is just C dV dt. So it's going to be C times this up here, minus 14 times minus 5,000 e to the minus 5,000 t plus 26 times minus 20,000 times e to the minus 20,000 t. Okay, so plug in for your C value. That was 0.2 times 10 to the negative 6. Do the multiplications here, and you'll end up with an expression that looks like this, I believe. 0.014 e to the minus 5,000 t minus 0.104 e to the minus 20,000 t amps. So that's I sub C of t. Up here we have I sub R of t. Now let's get back to I sub L. Well, here's something that you can do. I sub L of t has to be equal to minus I sub R of t minus I sub C of t. That's just that the sum of the currents leaving the top node is equal to 0. I put I sub r and I sub c on the right-hand side of the equation. So here's what you can do. You can plug in for your I sub r, and that's going to be, no, I just need to put the minus sign out front as well. That's because of that minus. But it's going to be minus 0.07 e to the minus 5,000 t plus 0.13 to the minus 20,000 t. Now minus I sub c, and I sub c is 0.014 e to the minus 5,000 t minus 0.104 e to the negative 20,000 t, like that. Okay, do the math, and I believe you end up with something like 0.056 e to the minus 5,000 t minus 0.026 e to the minus 20,000. Oh, yeah, 20,000 t amps. So there's another way to get I sub L of t. In other words, if you have two of these, you can get the third one based upon just this KCL equation there. All right, so we've pretty much got everything that we need. We've figured out the currents, we figured out the voltage. You could go with this and you could figure out the power dissipated by the resistor. You could figure out the energy stored in the inductor or the energy stored in the capacitor. You could go and figure those things out given these values. And of course, those are going to be time-varying functions, just like this is a time-varying function. Okay, so that completes the overdamped case for parallel RLC. So this is the natural response for the overdamped case. Okay, I'm going to stop this one here. We'll have another video for the underdamped case.